double check, make sure it is actually recording. Okay, very good. Okay, so getting back to the website. So you do have a homework assignment. It's not going to be using all that much time. If you already understand the concepts, this is the description of the homework. There are 4 questions involved, okay? Okay, so here we go. The first question is, just work on this one independent to the other 3 questions. So the questions are not related. Your answers should not be related. So independent to all other questions, pick at least 2 digits from the student ID as the domain X, okay? So if your student ID is 1112223, okay? You can take 1 or 3, 2 or 3, 1 or 3, you can take any combination. I think I checked and make sure that no student in this class has a student ID consisting of only 1 single digit. Like all zeros or all ones. I mean, that can happen. All ones can happen, but I don't think that happens in this class. Okay, so I think none of you have this problem. And any number of letters from your first name as the codomain y. Okay. Define a function f going from x, your domain, to y, which is a codomain, such that the function is not injective and not surjective. Yep.
So that last line, defining function such that it is not injective and not surjective. And maybe this is something that I should talk with you later, but the example I got, I have two members of the domain pointing to the same number, the same element in the codomain. That's not a function, right?
Okay, so you have to make sure that f is in fact a function first. So you have to think about what makes a function a function. So a function is really a subset of the Cartesian product between the domain and the codomain. But it has some extra constraints as well. So there's one particular constraint that makes a mapping, a subset of mapping, a function. So you have to kind of remember what that constraint is. So that's the first thing you have to do when you think, oh, this may be the answer. Check to make sure it is in fact a function first. Then you want to check to make sure it is not surjective and not injective for this particular question. Okay. The second question is pretty much the same thing, except the function that I want you to create is injective but not surjective. And you can probably guess what is the third one. The third one is it is not injective, but it is surjective. Okay, just basically flip from the second question. And then the fourth one is it is bijective. Bijective, once again, is both injective and surjective. So I just want to make sure that you can create examples of functions that are with these properties. Yep.
So that means that question we're looking for a function that is not bijective.
Well, not only is it not bijective, it is neither injective nor surjective. Okay, so let's take a look at all 4 possibilities, right? You have injective, you have surjective, right? So a particular function can be injective and surjective. That is called bijective. But all the other 3 possibilities are not bijective. So that means there are 3 ways not to be bijective. You can have a function that is injective but not surjective. That is not bijective. You can have a function that is not injective but it is surjective. That is not bijective. You can have a function that is neither, and obviously that one is not injective either. So injective only applies to this function. All other 3 are considered not bijective. Is that okay? All right. Okay, so this part basically just talks about how to answer the question. For each question, so which means you give me 4 of these things, the answer should look like the following. I'm using my name and ID as an example. And so I use X here as my domain. My domain has 068 as the 3 digits. My Y, or the codomain, has A, U, and Y as letters from my last name. And what I think is the answer, which is not necessarily right answer for any of these questions is a set that has two tuples in this case, 0a, 0u, 6y. Okay? Obviously, if you copy this, you're probably guaranteed wrong. Yes.
That isn't a function, right?
Exactly. It is not even a function. Okay? So if you're thinking, why is it not a function? It is a good time to review the material. No, I'm seriously, if you think, okay, but I don't know, how can you tell this is not even a function? It is time to review the material because the whole purpose of the homework assignment is to get you guys to understand the concept. It's a way for you to test, okay, do I really understand the concepts? If you're not sure, you can read the material, okay? But what if you say, text material is really cryptic and it's hard to read? Try other resources online. Try Google. Okay. If you just look, injective function using Google, you will find tutorials. You'll find videos to explain it. I'm not sure whether Khan Academy has anything like that, but on YouTube alone, I'm pretty sure there are at least 4 or 5 videos explaining what is injective, what is surjective, and so on. But there probably won't be one that will help you answer these questions directly because they don't know your name. Know your student ID. All right, so are there any questions about the homework assignment? So you're going to give me 4 things like this, okay? And for those of you who really want to kind of minimize how much time you spend on this, I'll give you a neat trick. Right-click, show math as, text command, copy this whole thing, paste it, just change the part that you need to change. Okay, do it 4 times, and if you understand the concept, should not take you a whole lot of time. Yes?
I tried doing exactly that, and it didn't work. It still had the...
You still need to insert the backslash open paren and the backslash close
I
paren.
did that too, and it still had it in that format.
Okay, so now I'm curious, why it is not working. I do have to sign in as a student to try this out, so I'm going to sign in using a different browser.
Zach,
Yeah.
I had a problem like that, but I decided to go to the insert equation, and when I did it, it worked out.
Huh. But if you do it directly inside the editor, it wouldn't let you do it.
Yeah, because it wasn't really showing the equation.
That is curious. All right. All right, so let me just kind of give it a try first, because I want to show you guys how you can get started on this one also. So I just signed in as a student. This is exactly what you should be seeing. So go to Functions and Relations, go all the way down to see the homework assignment, which is just simply called Functions. Click it, and scroll all the way down. Okay, so I'm going to do a copy and paste too. So I'm going to click this, right-click, copy the tag command here, Control-C, and then go to Add Submission. And that opens up a text editor, an HTML editor. And this is the one that I use, which is the ATTO, A-T-T-O, HTML editor. I'm not sure whether it has anything to do with this. So what I'll do is I'm going to give it a try. You do need to insert the backslash open paren and then do a paste. Oh, I think I know why. Because when you do a paste, it's also pasting in some other stuff. Okay, so here, this is kind of what you need to do if you want to use this approach. There are 2 ways to do it. For those of you who use Windows, which probably is like 95% of you, with the other 5% using Macs, right? So what you do is you open up Notepad, okay? So paste the whole thing into Notepad first, and then copy it from Notepad into Moodle. That will take care of the extra HTML, garbage, which is probably what is interfering. But I'm going to try this out once, just so that I can make sure that this does work. Okay, so I will finish this up by putting in the backslash open paren, and then also the backslash close paren, because you need those to surround your actual equation. Do a Control A, select all, Control C to copy, and then go back to the browser. Get rid of everything that I already have here, and just do a Control V. And this time it looks right to me, okay? At least it looks right. All the extra HTML code is gone, okay? Because I think when you copy directly from that small window, it automatically include formatted text tag in it, and that's why it shows the way it is. Okay, but the ultimate test is to save it and see whether it gets displayed correctly. So I'm going to save changes, scroll down again and see my own answer. So this time it does work. So that's how you can do it. But you only need to do this once, because once you put it into Notepad, you can either replicate it 4 times or 3 times in Notepad, or once you fix it once and put it into Moodle, then you can replicate it 3 times as well. Okay, but either way, it's not going to be that much of work. Okay, because I don't want you guys to do a whole lot of chore. I want you to show me that you understand what ejection is, what surjection is, and what bijection is. Okay. Are there any questions about the mechanical aspect of turning in the homework assignment, like what kind of editing you need to do, and so on? Yep.
Do we have to create new lines?
New lines.
Or
Okay, so the way it is right now, let me go back into the editor. It depends on how you encode the equations. So the way I did it was to use open paren to start the equation and backslash close paren to end the equation. So with this, what you can do is it's basically inline. So this whole thing here is really considered an item in line with your normal flow of text. So what you can do in this case is to say A1, okay, answer to number 1, and then you just copy this whole thing and just paste it here, paste it here, paste it here, and then change the other A1 to A2, A3, A4, and then make changes to your actual code. So if you do something like this, you save it, it will basically display on multiple lines with all the line breaks and stuff. So let me go back here. See, that's basically. Oh, I forgot something here. Probably a close paren. Let me fix that. Because if you don't enter your equations correctly, it will give you back, and it doesn't look right. So why doesn't it look right here? Doesn't.
Is it just because it's not displaying everything? I mean, everything.
Oh, because of the plus. Okay,
Yeah.
so we have to let it display everything because it's only using a part of my input. So if I do a plus, yep, that's it. Okay, very good. Are there any other questions about the mechanical aspect of your homework assignment? No other questions? Okay, so so this particular homework assignment is due. Oh, right there. It's due on Thursday, so you only have about 2 days to work on this. I don't think it will take that long, okay? I really don't think so, okay? I think it's going to take you, if you really sit down and work on this, and even including the time that you need to look up the words, the definitions of injection, bijection, and what is a function, it should take you no more than like maybe half an hour, 45 minutes at the most. Now, of course, if you're a Time Lord, like Doctor Who, then obviously you can cheat quite a bit here. Just use the TARDIS, go to the future, watch my future, lecture, go back in time, and put it in. How many people watch Doctor Who? Okay, some of you, okay. I just watched the episode where he explained which composer. There's a composer that he was kind of obsessed with, and he went back in time to meet the composer, only the composer did not exist. But he brought along all the albums, all the scores, everything goes thing that he knew about the composer with him back to the past. So he became the composer. And then in the end, he asked the question, so who actually wrote the music? Because he didn't write it, he just brought it back in the past. Okay, so that's the kind of show that Doctor Who is. It's really great. Da 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 da. Yeah. All right, so here's your homework assignment, and what we'll do today is to illustrate why functions are useful in computer science. And we are going to, well, we will talk about composition next, okay, because that's a little bit more boring. But I wanted to show you, I did show you this already, okay, the result of assignment operations, that's what we did last time, is to basically explain, how this eventually will allow us to go from the precondition of an entire algorithm step by step and derive the post-condition of an algorithm. If you know the desired post-condition of an algorithm, and you derive the actual post-condition of an algorithm, now you can compare the two. If they don't match, if they're not the same, then your program may not be doing what it is supposed to. Okay? On the other hand, if they match up exactly, then you don't even have to use a single test case to test your program, because you have just mathematically proven that your program is correct. Okay? So that's one application. So I'm going to show you the other application, which is kind of interesting too. It is related to the application that we have already talked about. Okay, so this is something that we are revisiting, because I kind of skipped over that earlier in the semester. Okay, so the question is, how do you express that an array is the effect of sorting? How do you express the precondition, and how do you express the post-condition of a sorting algorithm? That's the question. How? Yep.
Sorted, precondition is sorted or unsorted algorithm in an array.
You make no assumption when you are making the precondition. Okay, so the precondition really only has one thing to say, that is that you have an array, and there are so many elements in the array. And we are even allowing multiple, same value of reoccurring multiple times in the array. So there's really not much to say, right? You just have to say, okay, here's an array, each item is an integer or ASCII code or whatever you want, and there are so many of these. Okay, that's the only thing you can say. But given that as your precondition, how do you specify the post-condition of that array but sorted? Yep.
You have to first define if you're going to be ascending or descending.
Okay, so let's say we're dealing with, I think there's a way, I picked one particular method here.
Ascending, non-descending.
Non-decreasing. Okay, so it's kind of like increasing, but you can have equal values. Okay, so we are picking this particular order. So the question is, how do you express that? Now, you can think about this as, oh, that's pretty easy, right? We all know what is sorting, right? We all know how to tell somebody that, oh, this array is not sorted, but this one is. Okay, so let's go ahead and try this out, okay? Because I just want to point out the limitation of natural languages and how ambiguous it is and how much assumption that we actually use to fill in the details when we listen to something. All right, so let's go ahead and we'll talk about an array. I'm going to use the same terminology here. So we are dealing with an array A, and it has n elements. Okay, there we go. So I'm going to use my text editor here. It's not going to look nice, but for the most part, we'll be able to express exactly the same thing. So we start with an array A with n elements. Not guaranteed sorted. Okay. Now, not guaranteed sorted is not the same thing as saying it is not sorted. Because saying it is not sorted means it cannot be in the right order already. Something in it is out of order. Telling you that it is not guaranteed sorted means it might be already sorted. We don't know. Okay, it may be not sorted, maybe it's already sorted, we just don't know. Yep.
It's not guaranteed like the same phrase as random, I guess. Like it was put into the array randomly.
We don't know what it is. We just do not know how the elements are ordered. Okay. So this is the precondition. So I'm going to even label here. This is my precondition of the sorting algorithm. So I don't even care about the algorithm itself. For all I know, the sorting algorithm itself can be algor dancing, right? Algorithm. Okay, so magically when algor dances, the array gets sorted. All right? And by the way, this is not a political statement. Okay, I'm not into politics at all. Okay, so So I don't care about what goes between the precondition and the postcondition. I just want to know what is the proper way to say that this array is now sorted. Okay, that's all I care. How do we qualify that it is now sorted? Okay, so I'll go with the most obvious one. The most obvious one is to say, oh, a bracket 0, the first element, is going to be less than or equal to the second element, which is a bracket 1, which is less than or equal to a bracket 2. And assuming that we have not introduced the for all symbol, we just use dot 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 and then go to a bracket and minus 1 as the last one. Okay? All right, there's a big problem with this. There's no association of the values in the final array with the array that I started off with. If I want to create this condition, I can do it with a loop and I can do it really quickly. Let me show you what I can do to meet just this requirement. Okay? So in between, I'm going to use this algorithm for I equals 0, okay, int I equals 0, int I is less than n, plus plus I, a bracket 0 equals 0, oh, a bracket I, sorry, go equals 0. That will make the array meet that requirement, because now they're all zeros. Yes, they're all less than or equal to the next one.
Right.
Is that sorting?
No.
Well, okay, if this doesn't look like sorting to you, let me see if this one is better. Would that make it better?
No.
Now they're all different. It looks like it's sorted, right? Instead of 0, 0, 0, 0, now it's 0, 1, 2, 3, 4. Looks like it's sorted to me.
Sorting something is not what you originally had.
Well, you're not even sorting, you're deciding.
What am I missing? What is the description missing?
The elements should all.
They should all be here, right? Whatever I started off should still be here. Is that okay? That's what I'm missing. Okay, so let's say that is the case. So one thing you can say, okay, so now that we know, okay, that's not enough. Okay, this is a minimum. Okay, this kind of expression is a minimum, but it doesn't really quite express what sorting is all about. Okay, so let me see. What am I gonna do here? I know what to do. I'm gonna do this. Okay, I'm gonna use for all there exists, that sort of thing. Okay, so I'm gonna say. I'm going to use words here because I can't really use the for all symbol. So I'm going to say for all x in, okay, we can always give it a particular set. And just for shorthand, I'm going to use my, set x here is just going to be 0 all the way up to n minus 1, all the valid indexes, okay? And that's 1, yeah, that should be enough. Okay, so I'm going to say for all x in uppercase x, so this is all the valid indexes, right? There exists y in uppercase x. Okay, so I am now okay, I used the wrong open curly brace here. Should just use a open parenthesis. Okay, so now I'm using for all on the outside, which binds the variable x to something in x. But this, whatever I specified in the parentheses, should apply to everything that I can find in uppercase x. Is that okay? Because that's what for all does. Okay? Because whatever is inside the parentheses at this point applies to everything I can find in uppercase x. Inside, I use there exists. Now, there exists means I only have to find one thing, y, in x that meets the following requirement. Okay? And I'm going to say, okay, so I will change this so that we have, that's not going to work. I was originally planning to do something like this, but that's not enough either. Okay? That's not enough. Because to specify this, is not saying anything. There's no linking between the initial state of the array with the final state of the array. So one thing I have to introduce is a way to document what kind of values did I start off with before I do the sorting and start to change the elements in array A. Is that okay? All right? Okay, so I will have to put it into the precondition. So now with my precondition, I'm going to start with something a little bit more, okay, start with an array A, and I would use a particular notation, let's say V, okay? So I would just say that, okay, V bracket I equals A bracket I initially for all I in uppercase X. Okay? All right, so let's go ahead and read the precondition again, but this time with that extra thing here. Start with an array A with n elements. It is not guaranteed that it is already sorted. So the additional thing, which is V bracket I equals to A bracket I, is really just having a way to refer to the initial value of the array. Because this A bracket I is before the algorithm has a chance to change anything in the array. So I'm just locking in the values and call those V values. Are we doing okay so far? Okay. So V itself is not really a part of the algorithm. It is only here because we need to refer to those values when we are done. So with V here, now we can start to say something. Now we can say for all X in uppercase X, okay, after we sort the array, which is array A, each one of each item of array A has to be able to go trace its way back to an initial value that we start off with. Okay? Would that work? Would that, that on top of the other requirement, would that specify an array is sorted? Yep.
It would have a problem with duplicates.
It would have a problem with duplicates. Okay? In fact, it would have a problem just because now we can just pick one initial value from the entire array, replicate throughout the entire array, and that will meet this requirement. So once again, the concept of sorting an array is not captured. Okay? So you can try a lot of different methods, and it's kind of difficult until we get to the concept of a function. Okay? Why would I use a function in this case? All right, so here's the use. This is why I need to use a function. Okay, so instead of doing this, what I'm going to do is like this. Okay, so I would say if the array is sorted, then there exists a function f. Okay, and function f is bijective, such that. Okay, so these following are the constraints for this function f. Okay, so I go back and say for all. Okay, for all x in uppercase X. Okay, there exists nope. I think for all x is already that's all I need. So for all x in uppercase X, I only have to express the following. The final state of the array, which is A, okay, because A is the actual array that I'm sorting, okay? So I'm going to say X, A bracket X, okay, because that locks to a particular element of array A after the array is sorted. I'm talking about this particular element in the array, okay? It has to equal to, now this is the real trick here. It has to equal to V bracket F of X. Okay, what are we really doing here? Okay, a picture probably would be helpful. Okay, so I'm going to show you a picture next. This is the first requirement, and then we have to add the other requirement on top of this one. Okay, so the other requirement is just the other one. Okay, so I'm just going to copy and paste this one. Okay, this one is, we already know this one has to be there somewhere. Okay, so it's not this, but it's not the complicated one. Okay, the complicated one is the first one. So together with these two statements combined, now I am expressing what it means for an array to be sorted. Okay. Let's get rid of the stuff, or let's just kind of ignore for now the stuff that we already know and it makes sense, which is the second half, right? If an array is already sorted in a non-decreasing order, this condition has to be met. Any questions about that part? Okay, no questions about that part. So now we have to focus on the first part. In other words, we look at this part here and go like, okay, what is it really saying? Okay, so what we do is we draw a picture. Okay, we have an array V, okay, but V is not really used in sorting. It is only here to record the values of the array prior to the sorting process. Is that okay? Yep.
So Vx is the original array, or is that A?
Yes, so before the algorithm runs, V bracket I and A bracket I should be the same prior to the sorting algorithm runs. Okay. And that locks in the values of each element initially into a V element. And the indexes do match. Okay. So now you have, initially you have V bracket 0, A bracket 0, they are initially the same. V bracket, n minus 1, and A bracket n minus 1, they are also the same. That's the initial condition. Is that okay? It's really just binding the values of V to the initial state of A. That's what V is for. We run through some algorithm. The algorithm does not change V. It changes A, because we are sorting the array A, right? So when we are all done, we still have A bracket 0. We still have all the way up to A bracket n minus 1. Is that okay? But what is the function f doing? Function f is a map. It maps the indexes. It basically says, oh, this one, if I apply f of 0, it will be another index back to here. A bracket 1, f of 1 is going to map it back to here somewhere, and so on. In other words, it's basically spelling out and say each element of the end result of the sorting algorithm. If you apply f, you can find one and only one element from the starting state that matches it. Is that okay? So that combined with the second portion, which is the intuitive portion, explains what it means when we have when an algorithm sorts an array. The second part is easy. It's the first part that says, oh, you must have all the original values. That is difficult to express. Are we kind of doing okay so far? Because the objective of this discussion is just to illustrate the use of function. I did not tell you how to find a function, because that basically is the sorting algorithm itself. I'm just saying that there has to exist such a function if this algorithm is actually sorting. Are we doing okay so far? Okay, all right. And who would have thought, right? I mean, you guys think, sorting, that's easy. We talked about it in cisp440, and probably have examples of sorting algorithms throughout all the different other classes. But just to mathematically describe that an array is sorted is actually not that simple. Is that okay? I mean, is anyone kind of surprised or not? You come in kind of knowing this sort of thing. Mathematically, it's difficult to express something that seems intuitive to us. But why is this important? Other than I need something to talk about to take up like 45 minutes of this class. Why is it important? How does it relate to the other thing that we talked about in the previous class? Yes, we can go ahead. Exactly. Now that you have a target and say that this is the correct behavior of a sorting algorithm. Then you can apply what we learned in the previous class, and you derive the actual post condition of an algorithm. Quick sort, merge sort, bubble sort, I don't care, okay? If they get to the end and they can meet this requirement that we are just talking about, then the algorithm is guaranteed to sort correctly. Okay? It's because of that that we have to mathematically express what seems to be intuitive, and nobody really is asking, oh, what does it mean when something is sorted? We all know what is sorted, but can you prove it? Well, if you want to prove something, you have to be able to express it in a mathematical way. Is that okay? All right. Okay. So with this out of the way, so the notation, yeah, it is kind of long and tedious, but it's the idea that is more important. So now we can move on to how we can quote unquote stack functions. If you have taken calculus, and other math classes, you probably know this stuff already. So it should not be a long topic. This one is a fairly easy topic. It's more about notation than anything else. So if I give you a function f defined this way, f of x is 3x plus 5. I can break it up into two functions, two more primitive functions. I can break it into a function g of x, where I just triple the value of the parameter, and also another function called h, where we just add 5 to whatever the parameter is. So if I have these two functions, I can re-express f as a composition of h and g. Is that part okay? Does everybody understand the concept of how to nest the application of one function into another function? Okay, so you probably have learned this in your calculus class because you have to do this to take the derivative of a function. So the notation is really pretty much the same thing. I use this notation, which is probably what you use in your math classes. If g and h have inverses, then f also has an inverse. The inverse of f is basically the inverse of h applied on top of the inverse of g, which is the opposite of f itself. Okay, are there any questions about composition and how the inverse of the composite is expressed as the inverse of the components? Any questions about this? Anyone? All good? All right. This part is not really that complicated, so I'm going to move on. We'll talk about binary relation because it is really a part of the curriculum, but it's not really that special. Okay, so we'll go ahead and talk about what it is, and then you guys probably will realize, hey, there's another way to express binary relations. Okay, it's just that sometimes it's more handy to express it this way. So we'll go over the definition of what a relation is in this case. A relation, which is now considered as a set R over a set X, is a subset of the Cartesian product of X times X. In a way, it kind of feels like a function, right? Because a function is a subset of the Cartesian product between the domain and the codomain. Except in this case, you cannot have a codomain that is different from the domain. But wait, it's not even a function. Okay, it really is not a function. But it is a Cartesian product. So if I want to look at R relation as a set, I can just say that, oh, R is a subset. Not necessarily a proper subset, but it is a subset of the Cartesian product of X and X. X is no longer called a domain because we are not dealing with functions. X is really just a set where the relation is defined over. Is that okay? When we talk about a relation, you already know a lot of these relations. Less than is a relation. Greater than is a relation. Equal to is a relation. Okay? So it's about how an element of a set relates to another element of the same set. Okay? That's basically a relation. If an element x in the set X relates to another element Y in the same set, through the relation R, the notation is x r y. Just like x is less than y, x is greater than y, x equals y, and so on. So the relation is always in the middle because we are relating two elements. So on one side you have one element, on the other side you have the other element, and you basically say x relates to y through R. That's the notation. So once again, it sounds really abstract, but in reality, we define relations like less than, greater than, equal to, that sort of thing. When x and y, if those are sets, then you can also have x is a subset of, okay? X is a superset of, okay, and so on. It's a relation. Okay. Which also means, in this case, if x and y are related through relation R, it also means the tuple xy is an element of R when you look at R, the relation as a set. Okay, so that aspect is kind of like what we have been talking about functions, except these are not functions. Okay, they are called relations. You can also say xry is true if and only if xy as a tuple is in R. Okay, it's just different ways of saying the same thing. Okay, so these things or relations are used a lot in computer science because all comparisons can be seen as relations. So if you consider equality, okay, something is the same as the other thing, and you want to express R as equality over integers, then integers, okay, it becomes the set X. So R in that case can be defined as a set, okay, because we have the curly braces to indicate we are talking about a set here. An element of this particular set has to take the form of a two tuple, but not just any two tuple, okay? The first and the second item, they have to be the same because we're talking about equality. And each one has to be an element of Z, which is the set of all integers. So this is how we can define equivalence or equal to for integers. Yes?
Does that mean that we can't do x, y, where x belongs to Z and y belongs to another group? Say 2 equals 0 or 3
You cannot because relation is only relating elements of the same set. So if you are dealing with real numbers, then x has to come from the real number set, y has to come from the real number set. Obviously, equality works on real numbers as well, and also complex numbers. Okay. Now there are certain properties, just like injective and stuff like that, when we talk about relations. If a relation is reflexive, it means x, Rx exists for all x in the set. Okay, so let's take a look at this one, okay, because this one is, there's some hidden meaning that some people may not get just by reading just by looking at the math description. So I'll just go ahead and start with the math description here, and then we'll talk about what is implied but not really written explicitly. This says, okay, you can actually spell it out. It says, for all lowercase x in uppercase x, x Rx. That makes the relation R reflexive. What is not conveyed here is R can also relate different elements in a different way. In other words, this is just the minimum requirement to be reflexive. A relation can be reflexive and something else if it has some other stuff. I'll give you an example. So let's work with some examples here. And where's my editor? There we go. Okay. So I'll give you an example. So let's say x is ABC. Okay, ABC. Okay. And I'm defining the relation R as follows: AA, AB, BB, CC. Okay. So the question is, does this relation R meet all the requirements of being reflexive? What do you think? Yes. It does, right? Oh, but what about this thing here, AB? It doesn't make the relation not reflexive. Okay, this is extra. Okay, this is extra stuff on top of being reflexive, because reflexive simply means these items must be there. Okay, AA, BB, CC, they must be in relation R for R to be reflexive. It does not say anything about can it have other things. Yes, it can. Is that okay? Because the math description does not really seem to suggest that, but that's basically what it means. Are we okay with reflexive? Yep.
So basically, for any value in X, we can have any amount of two tuples, basically, for that set of X, I guess. Because it would look like you could have made like any set of two tuples if you have A, B, and C.
There's another way to look at this. It's more graphical, so for people who are visual, this may be better. Okay. So let's say you make a matrix out of the relation R. Okay. So on one side, we have A, B, C here, and then we have A, B, C here. Okay. And we'll go by column first and then row. Okay. So B, R, C is this particular cell. Okay. So I'll use a check mark to mean that that tuple does exist. Reflexive means this guy has to be there, this guy has to be there, this guy has to be there. But there can be other things too. If you like, if you can have this, you can have this extra one. It doesn't interfere with R being reflexive. Is that okay? It's just a more graphical way to look at things. Yep.
The relation isn't a function.
It is not a function. A relation is not a function, but there is a way to look at a relation, turn it into a function. I'll talk about that later, but a relation itself is not a function. Okay, so that's reflexive. The next one is symmetric. Symmetric is usually known as commutative, okay? So XRY implies YRX. Okay? So equality works that way. Inequality works that way too. Because X does not equal to Y implies Y does not equal to X. Right? Okay. So are there any questions about something being symmetric? Symmetric, graphically speaking, means that one side, if you look at this line as a mirror, okay? If something is on this side, the mirror image has to be on the other side. So if you want this particular relation to be symmetric, if X is over here, you must have another one over here, because it's the mirror image along this particular line. That makes it symmetric. Is that okay? Are there any questions about a relation being symmetric? Yep.
If it's reflexive, and it just has A, B, B, C, C for that example, is it also symmetric?
That is a good question. Because there's no requirement that X has to be different from Y. So the question is, in the actual definition of symmetric, is there an extra requirement that X and Y have to be different when we talk about this? That's a very good question. Let's look it up. So we are looking at symmetric relation. Okay, there we go. All right, so let R be a binary relation on A. Okay, R is reflexive if for all X in A, XX as a two-tuple is in R. Okay, so that part we covered. R is symmetric if for all XY in A, XY is in R, implies YX is in R. So that means,
I don't think it has to be different.
okay, there's no restriction. Okay, so could you ask your question again? Because I really want to just kind of make sure that I answer that question correctly. Go ahead. I think you're.
I just think that I was asking if you have a reflexive function where the only elements are AA, BB, and CC, is it also symmetric?
That particular relation, yes. Okay, so I'm glad that you confined it. Well, he used a function, but he should have used a relation. Okay, so if you have ABC and ABC, okay, and the relation, this particular relation is X, AA, BB, YY, okay, AA, BB, and CC, okay, not YY. It is both reflexive and symmetric at the same time. Okay? But I can make this one reflexive, but not symmetric. It's easy to do. I just have to add something here, but not over here. Is that okay? At the same time, I can make this symmetric, but not reflexive, just as easily. Because I can take out this one here, and add another one here. Now it is symmetric, but not reflexive. Is that okay? So one basically says, you must have all the diagonal elements checked. That's reflexive. The other one says, if you put a mirror on the diagonal line, then the mirror image has to match the exact set on the other side. So those two, one does not imply the other, because I can have a combination where something is this one, but not the other one, or vice versa. I kind of know my definition of symmetric is correct, but I just want to make sure. What? What just happened? Oh, you mean the number of tabs? Oh, this is not even bad. This is not even bad.
I don't think reaching the maximum number of tabs is what's necessary for being a bad number of tabs.
Well, on top of that, remember I'm using 1024 by 768. I'm not really quite using 1080p resolution. You have to see me teaching Android programming using Eclipse. Because when you have to look up, the classes, the interfaces, example code, and stuff like that, I easily opened up like 20, 30 tabs just to get one program to work. All right, so the next one is called transitive, which you already know what it is, okay? It simply means, if X or Y, okay, if X relates to Y, Y relates to Z, then R relates to Z. Greater than is an example, okay? If X is greater than Y and Y is greater than Z, then X is greater than Z. It works, okay? Equal to works too, right? Because if X equals Y and Y equals Z, then X equals Z. Okay? So there are quite a few relations that work out that way, which is transitive. Are there any questions about the definition of something being a relation being transitive? No questions? I'm not really sure whether transitive has a kind of more graphical way to display, because if A relates to B and B relates to A relates to B and B relates to C, then A relates to C. There's no actual easy way to graphically plot it. Yep.
You can show it just with the integers. 1 is smaller than 2 and 2 is smaller than 3, therefore 3 is smaller than 1. 1 is smaller than 2. 1 is smaller than 2.
Yeah.
And 2 is smaller than 3. Then 1 is smaller than 3.
Yes. I thought originally it said 3 is smaller than 1. Okay. Did I misheard or did you misspoke?
Yeah, I said it wrong.
Okay. Not that I want to point fingers, but sometimes I just want to make sure which end. Because I do that a lot too. All right. So equivalence is an interesting one. A relation R over a set X is equivalent only if and only if it is all three. Okay. So a relation is equivalent if it is reflexive, symmetric, and also transitive. Equal to is an example. Okay, because equal to is reflexive. Okay, 1 equals 1. It is symmetric. 1 equals 1 implies 1 equals 1. And it is also transitive. If 1 equals 1, and 1 equals 1, then 1 equals 1.
Wait, what?
There are very few relations that are that express equivalence. All right. So okay. So here comes the part where we can say, oh, relations can be expressed as functions, but it's not just using that notation. So I'm going to describe, how you can turn a relation into a function. Okay. I will actually go ahead and modify my notes here. So this way it is actually in the notes when you check it again. Thanks to technology, I can have a live textbook. Okay. So now I will talk about, relations turned into functions. All right. So the way you do this is you define a function. So given the R, okay, so let me start with some assumptions here. Okay, so we'll go ahead and say let R be a relation over a set X. Okay, so that's the assumption. It doesn't matter whether it is transitive or symmetric or whether it is equivalent or stuff like that. This works on all relations. So we want to define a function f that will express exactly the same thing as my relation. Okay? We can define a function f such that the following is true. Okay? So the first thing we say is function f is going to map, what do you think is the domain of this function? It is not just x, it's x times x. It's the Cartesian product of x. Okay? So if I go a little bit further, you guys will know exactly what it is. Okay, so x times x, lower uppercase, x times x is my domain. Right arrow. What do you think is my range? I just want to know whether something relates to something else. Okay? It's either there or not. It's either there or not. That reminds you of zeros and ones? Booleans. Okay? Booleans. So in this class, I just use 0, 1 to indicate it's false and true. Okay? So this basically, specifies, what is the domain and what is the range or codomain of this function f. But it doesn't really tell me the individual items of f. Okay? Okay. F is defined as follows. Okay. So $, okay? If you use $, it means it's going to be on its own. It is not in line with other text. Okay? This is on its own. So now we can say, okay, what exactly is defined in that function? And the answer is f is a set. Okay, we already know that f as a function can be seen as a set. Okay, so when we describe a set, we can either enumerate all the possible elements, or we can describe what one element looks like in the set. So that's exactly what I'll do here. It will be a two tuple. Okay, so we know each element of a function as a set, is a two tuple. But in this case, the two tuple, the first item of the two tuple itself, is also a two tuple. Now that makes sense because the range itself, or excuse me, the domain itself is already a Cartesian product. That accounts for the two tuple that is nested in the inside. The outside is accounting for how do we map an element of this Cartesian product into the codomain. So that's why it is nested. But that's okay. We'll go ahead and specify these things. So we'll just specify x as the first one, x, y is the second one, and z being the third one. Okay, these are just unbound variables at this point. So now we have to say, oh, exactly what is x and what is y and what is z. Okay. What do you think? there are several ways I can define this, but I'll go ahead and use this particular definition. So z equals to, so this is how the value z is defined. It's defined to be whether xy as a two-tuple is in the set of R, which is the relation that we are trying to re-express into a function. Okay, so I'm gonna turn this into the full view because this is a little bit harder to read, but I can turn this into a full view. Save and display. Go back there. Hopefully I did not make a mistake. Nope, looks good to me. All right. So this is how you can define, how you can turn any relation into a function. So let R be a relation over a set X. Okay, so then we already know that R itself is a subset of X times X, right? Because that's what a relation is. Is that okay? But we want to map it, okay, as a function f, since f is a function, we want to map x times x to 0 and 1, which is basically false or true. Is that okay? Now, that defines what is my domain and what is my codomain. But it doesn't tell me exactly what maps to 0 and what maps to 1. This one does, okay? So this one basically says each element of f, which is a function, is a nested two-tuple, where the first item is by itself a two-tuple as well. This part doesn't say what is x, what is y, and what is z. It's simply saying, okay, these are placeholders, and I'll describe what these placeholders have, or the properties of these placeholders. So this is really just saying, okay, these are placeholders of these three positions. This part is the most important part because it is telling you what is z. How do we come up with the value z, which can either be a 0 or 1, true or false, based on the value of xy? We know x has to be found in uppercase x, y has to be found in uppercase y, because this is coming from the domain. xy, if it is an element of R, because R as a relation is x times x as well. So if this element is found in R, z is 1. If this element cannot be found in R, z is 0. So I have just turned a relation into a function. Is that okay? Sort of?
You said uppercase Y. Did you mean like the
Uppercase one?
That's what you said, yeah.
Oh, uppercase X.
Okay, just okay.
Yeah.
Figuring out.
Okay. That's why I like typing and not talking. Especially this kind of thing. Any questions about this part? No questions? Okay. So everything, turned into functions, which is good. All right, so let's take a look at what we'll be talking about on Thursday. So you guys can kind of read ahead of me and get ready for that. We'll talk about set again, okay? So these are topics related to set one more time. But this time we talk about mapping and whether a particular set is countable or not, okay? So you want to read this. It's not long, okay? This is definitely not long, but it takes time to understand the content, okay? And you have to understand functions first, because this makes use of functions. It is all about mapping. We start off with a set of natural numbers, 0, 1, 2, and so on, okay? That's the set of natural numbers. So we start off with a set of natural numbers, and then we say, by definition, that particular set is countable. Okay, so by definition, it is countable. Guess why natural numbers are countable? Because they're also kind of counting numbers, right? Okay. So now the question is, how do we use this definition? The set of natural numbers is countable. How do we use this to qualify other sets and say that, oh, you know what? This particular set here, the set of all integers, is also countable. How do we do that? use a function. Okay, if you can use a function to map all elements of the set of integers into the set of natural numbers, if that function exists, is a one-to-one, okay, which means it's bijective, then the set of integers is also countable. That's why it's all about mapping. So some of these things is kind of easy because if you think about integers, it's pretty easy. Okay, how do you fold integers into natural numbers? Now you might think it may not be possible because integers go in both directions, right? You have a 0, 1, 2 on one side, negative 1, negative 2 on the other side. How can you fold it into one single direction?
Square root of the
Exactly,
squares.
it's just alternate. 0 maps to 0, 1 maps to 1, negative 1 maps to 2, 2 maps to 3, negative 2 maps to 4, and so on. It's kind of like knitting, okay? You're using one line to knit something else. Is that okay?
No. I don't understand. How does negative 1 map to 2 and 2 maps to 3?
Well, that's why you need to read this. I'm just giving you a preview in the next episode. You know?
This is
Okay.
a Doctor Who episode.
But the weird thing is rational numbers can also be countable. Irrational is a whole different game. Okay, that is not countable. But natural numbers are countable. I mean, rational numbers are actually countable. Then you go like, well, but we have a numerator and a denominator. How can that possibly be countable? In fact, if you have a two-dimensional coordinate system using only integers, that is countable as well. And the trick is this. Two-dimensional thing, you number the pixels in a diagonal. You go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. So now, given any pixel in this two-dimensional plane, what do? There is a natural number corresponding to it. What about three-dimensional? How do you deal with three-dimensional space? Same thing, except now you're filling in a diagonal plane instead of a diagonal line. Within the plane, you use this technique. So it works on any dimension as long as your coordinates are integers. Okay? So we'll talk about it in the next episode. But read ahead of me, okay? That's going to help.
Is that going to go for test?
Read the synopsis of Doctor Who before you watch it, yes.